Welcome to the Unit 4 Day 1 notes. Go ahead, pause the video, and classify these triangles by their sides and their angles. All right, so I'm going to classify them by their angles first just because that ends up sounding nicer. But for this first one, this is an acute isosceles triangle. The second one is equiangular and equilateral. And that third one, we have an obtuse angle right there. So it's an obtuse. And then since there are no congruent sides marked, it's an obtuse scalene triangle. So today we're going to start talking about isosceles triangles. We're going to start off with the parts of an isosceles triangle. There are a few different ones. We're going to start up at the very, very top here. This is called the vertex angle. All right. Now, let's start at the top. This triangle can be in any orientation. We know it's the vertex angle if it's the angle that's formed by these two congruent sides. These two congruent sides are called legs. So I think of it literally as like a stick person standing up on its own two legs. Hopefully your legs are the same length. I marked this angle with two markings just because I wanted to use one marking down here for these ones. These are each called base angles. And base angles are formed by one leg and the base of the triangle. So those are all of your parts. You've got two legs and a base, two base angles, and a vertex angle. So our base angles theorem says in an isosceles triangle, the base angles are congruent. So in this particular one, we have angle B is congruent to angle C. So if you look back at when I drew this, I marked those two angles congruent because of this theorem right here. So the way I find base angles is I find my legs, find those congruent sides, and then I cross to go to that angle. Those are your base angles. This does not tell me that that measurement and that measurement are the same. They cannot be. This is a linear measurement, and the angle is a degree measurement. So we are going to prove this. I don't know if I've said it in your class yet, but you can't use what you're trying to prove in order to prove what you're trying to prove. So since we're proving angle B is congruent to angle C, we cannot use that base angles theorem. So start off with what we are given. If you notice, we have segment AD drawn in compared to the last one. We did not have that. We can always connect 2 points because between any 2 points there exists one line. So I'm going to mark my picture with what I have so far. So I've got those are congruent and those are congruent. So step 2, I look for my reflexive side, which is what we have drawn in with AD. Now I've got two congruent triangles by side, side, side. So triangle ABD is congruent to triangle ACD because I have three sets of congruent sides. So finally, angle B is congruent to angle C by CPCTC. Anytime we prove triangles are congruent, the next step is always corresponding parts of congruent triangles being congruent. So I should double check that these two angles are in fact corresponding. The way I named those triangles, they were both the middle letters, so they are corresponding parts. So next up is the converse to the base angles theorem. Remember, converse is basically just the theorem backwards. So this says in a triangle, if two angles are congruent, notice it says just two angles, not two base angles, because at this point we don't know it's an isosceles triangle. So two angles are congruent, the sides opposite the angles are also congruent, meaning we have an isosceles triangle. So in this picture, I've got angle B is congruent to angle C. The side opposite of B is segment AC. The side opposite of angle C is side AB. So those are the two sides that are congruent. Again, the side measurement cannot be the same as the angle measurement. So segment AB is not congruent to angle C. That's not possible. So now we're going to prove that one. So again, you can't use what we're trying to prove in order to prove what we're trying to prove. So we're going to start off with step 1. I started writing step 1 where I should put an S for statement. We have angle B is congruent to angle C. And we have that segment BC is perpendicular to segment AD. All right, so all we can really mark right now is this. If two segments are perpendicular, or if two lines are perpendicular, then we know they form right angles. So angle BDA and angle ADC are right angles. Definition of perpendicular. Okay, perpendicular lines form right angles, so I can mark those as right angles. All right, now I've got two angles already. I have not said these are congruent. I've just marked them as right angles, so I should say they're congruent to be fully rigorous. So angle BDA is congruent to angle ADC because right angles are congruent all the time. So step 4, I said I already had two angles in each triangle, so I need a side. I either need the side between them, so BD and DC, or I need a different side. Well, segment AD is going to be our friend again. This is the reflexive side. So step 5, I can say triangle ABD is congruent to triangle ACD by, this time I'm going to start here and go angle, angle, side. Remember, the order of those letters matters. If you put angle, side, angle, ASA, that is incorrect. So anytime we prove triangles are congruent, our next steps are always going to be corresponding parts of congruent triangles are congruent. The side that we want, sides that we want are AB and AC, so we can say those are congruent. Again, looking in those triangles, first two letters, so they are in fact corresponding. Now we've got a special isosceles triangle. It's an equilateral triangle. Okay, it's called a special isosceles because an isosceles triangle needs to have two congruent sides. An isosceles triangle with three congruent sides is possible because it's got at least those two. So this has all sides are legs, and they're all bases as well. Okay, all angles are vertex angles and base angles. All right, so literally anything you look at has two possibilities. So this could be a leg or a base. All the way around. It seems kind of pointless, but what this enables us to do is use our isosceles triangles theorems in order to prove things or identify things moving forward. Okay, if you know something about part of it, you'd be able to figure out the angles and so on. Basically, just pick a base and then pretend that's a different value, even if it's the same. That's how you would use that. All right, so we've got a very simple problem where we need to solve for x and y. I'm going to start by drawing this as two separate triangles. When I draw my triangles and I split them like this, I try to keep them in the same rough orientation so that hopefully I can identify that, hey, these points and these points are actually the same place. So that means that's the same segment. So I know in triangle KLN I've got congruent angles, and I know I've got congruent angles down here. I know this is x plus 1. I know this is y, and this is 4. Now, in that triangle KLN, it's equiangular, which means it's equilateral, right? So another way I could think of it is these two angles right here are my base angles. So the sides opposite are congruent. So we've got y equals 4. That's the easy one to solve for right away. And I could extrapolate that and do that again with this angle and that angle to get that's a 4 right there. But NL is also in this triangle, and since this is an isosceles triangle as well, NL and LM are the same, so 4 is equal to x plus 1, so I've got x equals 3. Those are my 2 answers. All right, so you've got a little worksheet in OneNote to work on. If you want to write down a quick summary of what we talked about or any questions you may have, that would be a good thing to do. Hope everybody has a great day.